To lecture 4 on matrices, and today we're going to look at applications of matrix algebra. So last week we looked at finding the inverse of a 2 by 2 matrix and a 3 by 3 matrix, and today we are going to use the inverse to solve equations. So here we've got the applications of matrix algebra. So remember, I is the identity matrix. Remember, that's either like that, if it's a 2 by 2 matrix, or that if it's a 3 by 3 matrix, 4 by 4 matrix, 5 by 5 matrix, it would all be the same. Now, remember the identity just 1 through multiplication. So if you multiply A, the matrix A, by the identity matrix, you get A back. And same if you multiply it by the identity matrix on this side, you would still get A. Now, the reason I'm writing both of those is that, remember, normally in matrices, A times B or A times another matrix is not the same as that other matrix multiplied by A. Right, so order is important. Right, a couple of other things. A inverse multiplied by A gives me that identity matrix. That's what we used to prove that the inverse matrix we had was in fact the inverse, and then the same here. Right, so those are our little rules that we're going to look at just now. Right, so what I want to think of is we're going to look at something with normal algebra. Right? If I had something like 3x equals 9 and I wanted to solve that, I would just do that and my answer would be 3, right? But with matrices we cannot divide, right? So this would be impossible. Right? There is no such thing as dividing by a matrix. Right? It doesn't exist. So, if I have a matrix algebra, let's say I've got a big matrix called A, and that's multiplying a column matrix XYZ, for example, if it's a 3 by 3 matrix, or the column matrix XY if it's a 2 by 2 matrix. Right? And let's say that gives me a second matrix here, B. Right? So all that would need to look like, for example, is 2, 3, 1, 4. If it's 2 by 2, XY equals 4, 7, 3, 9. Right? That matrix is A. That's your so that's your coefficient matrix. That's your variables matrix, and that there is your answer matrix. In fact, I'm going to make my answer matrix 2 by 2 matrix, 2 by 1 matrix. Right. Now, you can't take that over and divide by it, it's impossible. Okay? So, thinking about it like that, it wouldn't work. But, if I start with my original equation, matrix equation looks like that. Now, I want to be left with x equals something. Right, that's the dream for solving any type of equation. So, what I'm going to do is, I'm going to take the inverse matrix of A and multiply the left hand side, because remember, order is important, of both terms of my equation by inverse matrix A. Okay? Now, I know from here that the inverse matrix times the normal matrix gives me an identity. So that would give me the identity times matrix X equals A inverse B. Right? Now again, from my rules, if I multiply the identity matrix by another matrix, that's just the same as multiplying that matrix by 1. So that's just going to stay X. So that means that X is just equal to A inverse B. So all that tells me is if I want to solve a matrix equation, I need to multiply the left-hand side of the answer part of your equation by the inverse matrix of the coefficients of the left-hand side of your equation. Now that sounds like gibberish. It's not. Let me show you how it works. Right, that's just the theory behind it. You don't need to worry about that. I'm going to go off and do a proper example. So all we're going to do is we start with our matrix. We're going to make up a matrix equation. If we multiply the left-hand side by the inverse matrix of our coefficient matrix here, we will get the answer to our equation. Right? Now, where you'd have seen this before, but doing it in a different method, would be simultaneous equations. So effectively what it's going to do is it's going to take simultaneous equations and turn it into a matrix algebra question. Now, if it's a standard simultaneous equation with 2 variables, you wouldn't do it, but with 3 variables, that's when you would choose to do it. Right, so example number 1. Solve 2x take away y plus z equals 5. X take away 3y plus 2z equals 2, and 2x plus y plus 4z equals negative 3. Okay, so I've got a system of equations. Now you might say, well, what's that got to do with matrices? So what we can do is we can turn that into a matrix equation, right? So the variables that I've got are x, y, and z. Right, in all 3 equations, x, y, and z. So 3 equations, 3 unknowns, right? Then here is where I put in my coefficient matrix. So all the numbers, they go in front of each of these terms. That's 2, negative 1, 1, 1, negative 3, 2, and 2, 1, 4. And then I'm going to put my answer matrix here, which is 5, 2, negative 3. Right? So my piece of matrix algebra told me, right, if that's A, and that's X, and that's B, right, then X is the inverse matrix of A multiplied by B, right? So that tells me that, so I'm just thinking about this in terms of A and B. So if I think about it in terms of my matrices, that means that X, Y, Z is going to be the inverse of this matrix here. Okay, the inverse matrix of that multiplied by B, which is my answer matrix here, 5, 2, negative 3. Okay, now if you have a computer can calculate an inverse matrix in no time at all. an absolute fraction of a second. And then it would just multiply it by that, and it would find you your x, your y, and your z in a split second. But we're going to do it by hand. So that means I want to find out what this matrix is here, right? So let's have a look at what we do, right? So I'm going to call, or I've already called, my matrix A to be 2, negative 1, 1, 1, negative 3, 2, and 2, 1, 4. Right. And what I want to do is find the inverse of that matrix, because I know if I find the inverse of that matrix, I'm done. Right, so we know from last week this takes a little bit of time. So first of all, we find the determinant of A. So that means we expand along the top row. So that's positive 2, take away negative 1, plus 1. And then remember, we create minor matrices. So those wee squares are minor matrices of the elements not on the row and the column of the coefficient. So this one here, not in the row, not in the column, negative 3, 2, 1, 4. Right, the corresponding element here, negative 1, so not in that row, not in that column, 1, 2, 2, 4. And lastly, 1, not in the row, not in the column, 1, negative 3, 2, 1. And remember, we just do AD, take away BC, so that's negative 12, take away 2, that becomes plus 1, 4, take away 4, plus 1, 1, take away negative 6. So that gives me 2, and that there is negative 14. Plus 1 times 0 plus 1 multiplied by 7. If you put that all together, it gives you a determinant of negative 21. Right. So then we want to find that big cofactor matrix of A, which means we're going to have, that's a big matrix with made up of those 9 minor matrices from the original matrix A. So, and you remember we put our signs in front, so plus, minus, plus, minus, plus, minus, plus, minus, oh, minus, plus. Right, now, so we're looking at matrix A, so I'm going to get that back, hopefully. Yeah, I'll move that up here, you can see. Right, so again, we're making minor matrices just like we did in the determinant. So we're doing it for this one, which is the top left-hand element. So not in that row, not in that column. So negative 3, 2, 1, 4. Right, then we're in the top, in the middle. So not in that row, not in that column. 1, 2, 2, 4. And then we're in this element here. So not in that row, not in that column. 1, negative 3, 2, 1. Then this one here corresponds with this element here. So not in that row, not in that column. So negative 1, 1, 1, 4. Then we've got the middle element. So not in that row, not in that column. 2, 1, 2, 4. And then here, we've got this element here. So not in that row, not in that column. So that's 2, negative 1, 2, 1. Right, so we're just creating these minor matrices. If you spot a mistake in anything I'm doing, please let me know, because with matrices it's probably the area of this part of maths you'll make the most mistakes with. Right, so then we're down here, so not in this row, not in this column, so negative 1, 1, negative 3, 2. And then we're in this element here, so not in that row, not in that column, so that's 2, 1, 1, 2. And lastly, this element here, so not in that row, not in that column. So 2, negative 1, 1, negative 3. Okay. So that's my matrix of minors. Now, when we've got minor matrices with lines on either side and they're 2 by 2, all that means is find the determinant for 2 by 2 matrix, which we know is AD subtract BC. And you can miss that step out if you want. I'm just showing you all the working I possibly can, so that hopefully there's no room for misunderstanding. Right, so here, negative 12, subtract 2. 4, subtract 4, and 1, take away negative 6. Then we've got negative 4, take away 1. 8, take away 2. 2, take away negative 2. Watch the double negative there. And negative 2, take away negative 3. Then 2, oh sorry, 4, take away 1. And then negative 6. Take away negative 1. And hopefully you can see where all that stuff has come from. Right, so now it's just a case of simplifying that down. So we've got negative 12 take away 2, it's negative 14. 0, 7. Negative 5 plus 6. 4 plus 1, subtract 3 plus negative 5. Okay, so I've just calculated those elements, and then lastly I'm just going to make my final matrix. I'm just going to take into account that. So positive and a negative sign next to each other stays negative. 0 is negative 0 and 0 are the same thing. Plus 7, so that's 7. Two negatives next to each other, we know right next to each other make a positive 6, so 5. Positive 6, negative 4, positive 1, negative 3, negative 5. And then we know we want to find the adjoint matrix. And all we do is we transpose the matrix we've just worked out. So we swap the rows and make them the columns. Okay, so we work out that adjoint, which just means we find the little transpose. So negative 14, 0, 7. So that first row becomes that first column. Then that second row becomes the second column. And then lastly, the bottom row becomes the final and third column. So there we go. And then remember, A inverse is 1 over the determinant, so that's negative 1 over 21, and then that matrix stays the same. And remember what I said, you can either absorb then the 21 into the matrix, or you can just leave it as it is. I tend to leave it as it is, especially if I know I'm using it again later on. Because remember, the formula for the inverse matrix is 1 over the determinant, so it's 1 over negative 21, multiplied by that joint, and that joint just sits there. Right, so if I look back at the theory from what I did earlier, right, I want to know what elements x, y and z are, right? And the way I do it is I'm told if I multiply the inverse matrix of this by those values there, right? So x, y, z is equal to 2, 1, so 2, negative 1, 1, 1, negative 3, 2, 2, 1, 4. The inverse of that multiplied by 5, 2, 3. Right, that was what my theory was behind this. So x, y, z is just the inverse matrix of this is this thing I've worked out here. So negative 1 over 21, negative 14, 5, 1, 0, 6, negative 3, 7, negative 4, negative 5, multiplied by 5, 2, 3. Right, I'll move that up a little bit. The screen turned off the computer there. Right, okay. So the inverse of that matrix I worked out in the previous step, and I got it to be this thing here. So I'm told that the answers x, y and z, like simultaneous equations, so we can check them at the end, is if I multiply the inverse matrix by that, what I'm calling the answer column matrix. The answers to the 3 simultaneous equations at the start. So I need to do matrix multiplication. Right, now that's a 3 by 3 matrix, that's a 3 by 1 matrix, so tick, good for us. We know those matrices are going to multiply together. So I know I'm going to get one big long column matrix that looks like that. Hopefully I've left enough room. Maybe not. So, in fact I definitely haven't. Let me just change that, right. So it's just one element in each column. Sorry, one element in each row. Right? I'm just doing it because I know I've got to multiply, do matrix multiplication. So I know that's row 1, column 1. That's row 2, column 1. And that's row 3, column 1. Right, so that means I need to multiply row 1 by column 1. So that there is negative 70 plus 10 plus 3. And remember you add the elements together. So negative 70 plus 10 plus 3. Right, then we're doing row 2 times column 1. So 0 plus 12 plus negative 9. Then here, 35 plus negative 8 plus negative 15, like that. Right, so So here, negative 70 plus 10 plus 3 is... It's been a long day. Oh, sorry, that should be what I missed out here. Something that doesn't look right. I've copied that answer matrix down wrong from the original question. That's what's up. Right, so work that out. I get, so that's a negative. So I get that to be negative 63. I work these out, add these together. Same issue, that's going to give me a plus this time. It's going to give me a plus this time. Right. So add those two together, I get 21. And if I add all these up together, I get 42. Right. Multiply these two things together. So that's 63 over 21. Negative 21 over 21. And 42 over negative 21. So just multiply that by that, that by that, and that by that. So that tells me that x, y, z equals 3, negative 1, negative 2. Just like that. 63 divided by 21 is 3. Negative 21 divided by 21 is negative 1. And 42 divided by negative 21 is negative 2. Apologies for the little mistake. I just copied over the first bit. I'd copied that over as 3 instead of negative 3 from the question. Happens. You know what I'm like. I'll make mistakes from time to time. Right. So that means that x equals 3, y equals negative 1, and z equals 2. Right. Now let's look at our original set of equations. See if that works. Just like we would do at Nat 5 when we're checking normal simultaneous equations with 2 variables rather than simultaneous equations with 3 variables. Right, so let's see if this works. So I'm saying that x is 3, y is negative 1, and z is negative 2. So let's substitute that in. So if I put that in there, I would get 6. If I put that in there, it would be plus 1. So 6 plus 1 plus minus 2. Yep, that's 5. So it works for that equation. Right, if I substitute those into that equation, I get 5. Let's try the next one. So 3 plus 3 is 6. Subtract 4 is 2, so that works as well. And then if I substitute them all into this one as well, that would be 6. Take away 1 is 5. Plus negative 8 is negative 3. So I have solved that system of simultaneous equations using inverse matrices. Right, now there's a second method that a few of you might have done in advanced higher before called Gaussian elimination. We will get to that, but I think this is a little better because you can use a computer a little bit more easily. It's all to do with matrices, it's all to do with algebra rather than just number systems. But hey, each people can use whatever method they want to solve systems of equations. Right. Let me go on and do it. Okay, let's look at a second example here. So I'll just get rid of this stuff. Right, and hopefully I'll not include as much theory in this, but I'll just show you how to get the answer. So, example 2. Right, so this is my system of equations. Again, you've got 3 letters you don't know the answer to, x, y and z, so that means I need to have 3 equations so that I can deal with that. So I've got 3 equations and 3 unknowns, which is exactly what I'm looking for. So, first of all, I'm going to set up my equations, my matrices. So, my variables, x, y, z, and my coefficients, 3, -4, 1, 1, -2, -2, and 1, 1, 1. And then my answer matrix is 24, 7, and 4. Right, so that means if I take the inverse of this matrix over to here, if I multiply the left-hand side of each side of the equation, so if I multiply here by the inverse of that matrix, I'll get rid of it, so it goes in that side of that matrix as well. That's 3, -4, 1, 1, -2, and 1, 1, 1. And it's the inverse that I need to take because that's the matrix equivalent of dividing. Multiplying something by its inverse is the equivalent, but we've got to watch we do it on the correct side, so we've got to think through what we're doing. Right, okay, so that's the theory. So this is what I want to find. So again, I'm just going to call that matrix here A, that matrix here X, that matrix here B. Right. I don't need to worry about it, I'm just going to call, the only one I need to worry about this here is this A. So, A equals 3, right, so I want to find the inverse of this matrix here. Right, the inverse, I'm just calling it A. So, first thing I need to do is find the determinant of A. So, let's expand on the top line. So remember, always goes plus, negative, plus, because of our matrix of signs that we're expanding along. Right, so okay, let's just check that's right. So not in that row, not in that column, not in that row, not in that column, not in that row, not in that column. Just checking, you see something, if you get 2 minor matrices that are the same, most of the time we've done something wrong. In this case we haven't, that's why I was just double checking here. Right, so we're just doing our usual AD take away BC. So that's 2, -2, take away -2. That's 1, take away -2. And that's 1, take away -2. Just checking that makes sense. It does, right. So that's 3, and that's going to be 0. 3. Right, so that's 12. Take away 3, so the determinant of A is 9. Okay, my writing seems to be getting even worse today. So, we find the determinant by expanding across our top line, remembering our matrix of signs, finding the minor matrices, and then doing AD minus BC in each part. Right, so then I need to find my cofactor matrix. that's a big horrible matrix. Right. Doing that. Right. And then we're just putting our minor matrices in. Right, so from here. So that there is -2, -2, 1, 1. 1, -2, 1, 1, and then 1, -2, 1, 1. Then here, not in this row, not in that column. So -4, 1, 1, 1. Not in this row, not in that column. 1, 1, 1. And then here, not in this row, not in that column. 4, 1, 1. Right, then not in this row, not in this column. So this is going to be a bit more tricky. Then not in this row, not in this column. And then not in this row, not in this column. Right. Okay, so I've just made my cofactor matrix of all those minor matrices, and I've just made the setup of what happens. Remember, minor matrix, AD take away BC, so that's -2 take away -2, that's 1 take away -2, and that there is 1 take away -2. Right here we've got -4 take away 1, 3 take away 1, and 3 take away -4. Here we've got 8 take away -2, -6 take away 1, and -6 take away -4. Just like that. So plus 0, subtract -3 plus 3. So just simplify that down. That gives you 0, that gives you 3, that gives you 3, gives you -5, gives you 2, gives you 7, 10, and -2. Let me just check those numbers. I hope those are right. There we go. So just simplify those down as much as possible. So 0, -3, 3, 5, 2, -7, and 10, 7, and -2. So that's your cofactor matrix of A. So you want to work out the adjoint. So we just swap the rows and our columns together. Like that. Right, so that means that A inverse is 1 over the determinant, which I worked out to be 9, multiplied by 0, 5, 10, negative 3, 2, 7, 3, negative 7, negative 2. Right, but let's go back to start an example. So that's my inverse matrix. So that's what I needed to do. X, Y, and Z were the inverse matrix multiplied by 24, 7, 4. So that means in our case, X, Y, Z is the inverse matrix, which is this thing here. So 1 over 9. And we're multiplying that by 24, 7, 4. And I'm hoping for whole answers here, or whole number answers. We shall see. Sorry, I just stopped a minute for just to check something over here. It didn't look like it was right. I've made a mistake. C in the determinant of A. Here, most of you hopefully will have spotted that. That's not a negative one like I've got there, it's a positive one. So that should be 12 plus 3. It should be 15. Right, so the determinant was 15, everything else was right. That's just me being daft here with our double negatives next to each other. In fact, it was actually copying more from one line to the next because the double negatives were right, it was the plus for some reason became a subtract. Anyway, right, apologies for that. So that means that really we've got 15 here and we've got 15 here. Right, so hopefully you spotted that as I was going along. If you did, fantastic. If you didn't, then well, you're in the same level as me at the minute. Right, so so remember, same thing, that's a 3 by 3 matrix, that's a 3 by 1 matrix. Those are the same thing. So that means that we can multiply. So we're going to get a big column matrix with just one big calculation in each column. So that's row 1, column 1, row 2, column 1. It's got to be column 1 because there's only one column. And row 3, column 1. Again, you don't need to write those if you don't want to. Right, so I'm multiplying row 1 by column 1. So that's 0 plus 35 plus 40. That's negative 72 plus 14 plus 28. Good. And then 72 plus 49 subtract 8. Sorry, subtract 1. Plus 8. Okay. So that gives you 75. That there gives you 30. Negative 30, and that there gives you 45. So it gives you 50. Check 72, 72, 49. Yep, melt down again, 15. Right, so you absorb those in. So 75, negative 30 and 15, you absorb that in, so that's 75 divided by 5, which is 5, negative 30 divided by 15, which is negative 2, and 15 divided by 15, which is 1. So x is 5, y is negative 2, z equals 1. Okay, so that's using matrices to solve systems of equations, right? Now, make sure you know how to do that. What I'd like you to do is look at questions 4 to 6 on page 6 to 8 of the matrix book. Now, if you look at those questions, it says, do these questions using Gaussian elimination. I don't want you to do it using Gaussian elimination just now. I want you to try those 3 questions using what we have done today. The answers at the back, you'll get the same answers, and then tomorrow, or maybe the start of next week, I will do Gaussian elimination for you. Okay, I apologise for the couple of mistakes that happened there. It happens, as I said, when you're calculating matrices. It can happen, you forget a negative sign, you make a mistake in your calculation from here to there, but don't worry too much about it. The great thing about these days is we've got computers that can check to see if we're doing these things right. But what I'm interested in is that you know the theory behind doing it and that you can work them out.